In this video, we'll talk about the transformations of functions. And we transform a function. What that really means is we're going to either do four things to a function. We can make the function slide left and right. That's one thing we can do. We can either make it go up and down, slide up and down. We can make it either shrink, or we call it compressions, or we can make it expand, and it's called a stretch. Or we can flip it. That was called reflections. So based on that, we start off with this general transformation, and this is for any function, and pretty much every function is going to look like this. But in this general function, these values that are highlighted in different colors are the things that are going to change the function. And every function that you deal with will have what's called a parent function. For instance, if we start off with the quadratic function, which is f of x equals x squared, I can develop the parent by taking some x's and some y's and just plugging them into the equation. Remember that this letter f of x, this is just really y equals. That's y equals x squared. So if I give x values, such as -2, -1, 0, 1, and 2, if I plug these numbers into this equation right here for x, I get back a y. So I get back -2 squared, or -2 squared is just 4, -1 squared is 1, 0 squared is 0, 1 squared is 1, and 2 squared is 4. And so when I graph this function here, and I plot those points, so when I plot these points, here's what I get on this function: 0, 0, 1, 1, 2, 4, -1, 1, -2, 4. I get the parent, and the parent is this right here. This is called the quadratic function. It's based off the parent of f of x equals x squared. Now, what will happen is I can move these points by rearranging this h and this k value, adding an h and a k value and an a value. Generally speaking, we start off by moving them left and right and up and down. In this particular equation, for instance, if I rewrite this using the quadratic's general form, which is f of x is equal to, I'm going to leave a alone, leave it as 1, so I'll just do x minus, let's do -3 squared, because it's a quadratic. That means I'm squaring it, plus, let's do plus, let's make k 5. So what this is going to do is, it's going to shift every x value to the right by 3 units. And the reason that it's shifting to the right is because when we talk about this, remember from the general form of the equation, we talked about the general form. The general form has this negative here. And just like when we talk about circles, this negative is going to flip things around. So a -3 actually is going to move it to the right 3, because you're applying it to the x's, and the x's are going to shift to the right. Likewise, a +5 here, when it's on the outside, well, this is saying, once I calculate all of this, and I'm not applying to the x anymore, I'm applying this to the final thing, which is your y. So it's going to add 5 to the y's. So essentially what you're doing is, when you look at this transformation, you are shifting the graph to the right by 3, always opposite of x, and up by 5. And what you can do is you can start off with the parent, and what this literally says is to get the new function, the transformation function, this says to add 5, or add 3 to every x. That's what right 3 means. So now the new x's are -2 plus 3. -2 plus 3, that's going to be a +1. Then -1 plus 3 is a +2. Then 3 plus 0 is this. Then 1 plus 3 is this, and 2 plus 3 is this. Here are your new x values. Then when you shift the graph to the right by 3, those are the new x's. And this has to add 5 to all the y's. So 4 plus 5 is 9. 5 plus 1, or 1 plus 5 is 6. 0 plus 5 is 5. 1 plus 5 is 6. And then 4 plus 5 is 9. And essentially what you've done is you've taken each one of these points. For instance, you started here at 0, 0, and you shifted it to 3, 5, because it moved the graph up 3 to the right 3, and now we're going to move it up 5. Let's go up 5. And so now you're sitting at this new point here, 3, 5. And so this new point moved over here. And notice that negative 1, 1, and 1, 1, they've both shifted. This one shifts to 2, 6. So again, we've taken this point right here and we moved it over 3. 1, 2, 1, 2, 3, and up 5. And you got this new point, 3, 6. We've taken this point right here, 1, 1, and we moved it over 3. 1, 2, 3, and up 5. So you get that new point, which is 4, 6. And the same thing happened with the other points. So you get the same graph, but the graph has now been shifted. So all transformations do is they move things left and right or up and down, or they can also stretch and shrink them. But when we stretch and shrink them, right, again, it's just looking at what this value, the value in the front A is going to tell me whether the graph stretches or shrinks. It also tells me whether the graph flips or not. And what I mean by that is if A is A, let's talk about stretches or shrinks. A stretch is when A, or the absolute value of A, is greater than 1. A shrink is when the absolute value of A is in between 0 and 1. And you may see a shrink called a compression. It's called a compression. And you may see a stretch. And when we compress something, actually we make it flatter, by the way. Make this flatter. Think about compressing a can. If you're looking at a cylinder, when you have a cylinder, if you compress it, you push down, it makes it flatter. When you stretch something, imagine pulling a cylinder up, it makes it narrower. So a stretch makes something narrower, a shrink makes something flatter. But when you talk about this, if your A value is greater than 1, the absolute value, because if you have a negative, we'll talk about that too. And when you have a negative A is a reflection. It's a reflection. It's a reflection over the x-axis. It's a reflection over the x-axis. So it flips it down if it was in the top, or it flips it up if it was in the bottom. But it's a reflection over the x-axis. And so all of these things in the equation are going to move the graph some kind of way. So let's do another example. And so we had the example on the homework of, you guessed that as f of x is equal to x squared plus 5. And I want you to realize that the parent here, the parent function is x squared. So we have a quadratic. And what we're going to do to this quadratic, remember x, y, and we have negative 2, negative 1, 0, 1, and 2. And I always start off with these points when I transform. And I know the parent is 4, 1, 0, 1, and 4. And now this plus 5, well, what is this plus 5 doing to the graph? Because it's not inside the parentheses, it's not affecting x. It's only affecting y. So essentially what I'm doing is I'm going to move the graph up by 5. And so what you can really do is start creating these things we call rules, where I take the point x, y, and how did I transform it? Well, here, x's did not change at all. And for every y, I added 5. For every y, I added 5. So what this is saying is then if I make my new graph, my x's do not change. So negative 2, negative 1, 0, 1, and 2. And I'm going to add 5 to every y. So I get 9, 6, 5, 6, and 9. So take every y. So take 4, plug it in here. 4 plus 5 is 9. Take 1, plug it in here. 1 plus 5 is 6. So if I plot these new points, then that'll give me my new graph. So when I plot these points, we have 9 out here. I'm sorry, we have negative 2. That's what I'm trying to be at. We have negative 2 here, positive 2 here. We have 9 up here, 6 here, 5 right below it. So rough sketching this, negative 2, 9 here, 0, 5 here, 1, 6 here, 2, 6 here. Here's the parabola that I want to graph of that. All right. And when you do this, then all this is saying is that if you can actually tell me in words what the transformation is, then you can always write a rule. So another example would be something like this. F of x is equal to 3 times x minus 4 squared plus 2. Notice everything in here is doing something to the graph. The 3 is going to, since the 3 is greater than 1, it's going to stretch the graph. It's going to stretch. And when we stretch the graph, we stretch the y value. We're stretching the y value. Because notice it's not affecting the x. It's going to stretch the y's. However, this 4 inside of here is going to affect x. And it's always opposite. So if it's a negative 4, I'm actually moving right 4. X always moves opposite of its sign. And then the plus 2 is going to move the graph up 2. And so again, what I can do is I can start off with my parent, which is -2, -1, 0, 1, and 2. And here I get 4 again. And remember, the parent for this is the x squared function. It's f of x equals x squared. It's the quadratic. So I'm plugging in those values, and I'm getting these y values again. 1, 0, 1, and 4. And then I can write a rule for this. And my rule is, well, look, when I do this, the only thing affecting x is this right movement, the horizontal movement is affecting x. These other two movements, the stretch of 3, means you're going to multiply every y by 3, and the up 2 means you're going to add 2 to every y. So when I write this, I'm going to stretch it by, I'm going to first worry about the x's, right 4. So that's x plus 4. Then I'm going to stretch it by 3, so that's 3y. Stretch every y by 3 means multiply by 3, and then add 2. And here's the rule that I can use to write it. And so when I write this rule, and I make my new points, x and y, my x's, every x got added to by 4. So -2 plus 4, positive 2. -1 plus 4, positive 3. 0 plus 4, positive 4. 1 plus 4, 5. 2 plus 4 is 6. So here are my new x's. And then my y's all got stretched by 3, so I'm going to multiply every y by 3. So 3 times 4, 12, and then add 2. That's 14. 3 times 1, 3, add 2, that's 5. 3 times 0, 0, add 2, that's 2. 3 times 1, 3, add 2, that's 5. And 3 times 4 is 12, add 2, that's 14. So here are the new points. All I have to do is plot those points, and I can graph this equation.